Let's talk about the properties of continuity. These are four very key properties that are almost common sense. If b is a real number and f and g are continuous at x equals c, then I can take this real number and multiply it by my continuous function, and that does not change its continuity. I can add two continuous functions, and that function is also continuous. I can multiply two continuous functions, and that is also continuous. And the one that gets a little confusing is the quotient one, because I can take the ratio of two continuous functions, and as long as g is not 0, then this quotient is also continuous. Now, some functions are always continuous at every point. Polynomials are always continuous. Rational functions are always continuous as long as q is not 0. Radical functions are continuous within their domain. And the trig functions are always continuous within their domain. Now, tangent, cotangent, secant, cosecant, we do have to check the domain usually. So if I look at this function right here, f of x is x plus sine, I want to identify the domain. And the domain of f of x, in this case, is all reals. Now, these are both one of the four types of functions we have already said are already continuous. So you don't have to do anything else. You can simply say this is continuous over its entire domain. Now, the same thing for f of x is 3 tangent. This is continuous over the entire domain of tangent, which means we will be leaving out these pi over 2 minus pi over 2, etc. Now, this function, this is the quotient rule. This function is continuous over its entire domain, and this function is continuous over its entire domain. However, cosine is 0 at pi over 2 minus pi over 2, and then adding the odd multiples after that. So this is continuous over the entire domain of the function, but you see where cosine is 0, the function's not defined. Let's look at some composite functions. If g is continuous at c and f is continuous at g of c, then the composite function, f of g of x, equals f evaluated at g of x, is also continuous. So you can take one very nice continuous function, stuff it into another very nice continuous function, and voila, you get out a continuous function. So let's look at tangent. Tangent is, let's look at what is its domain. And its domain is, of course, I'm circling my undefines here. Tangent is undefined at x equal pi over 2 plus n pi. Now, a lot of times, I will write it this way, pi times n plus 1/2. All right, so this function is continuous at all points within its domain, and if I wanted to write out what they were, and sometimes we want to do that, you can start back a ways. So let's try minus 3 pi over 2 to minus pi over 2, put in a comma, minus pi over 2 to pi over 2, put in a comma, pi over 2 to 3 pi over 2. So this is how you write it so that you're eliminating those discontinuous points. Now let's look at this function right here. G of x is sine of 1 over x when x is not equal to 0, but it is equal to 0 when x is 0. So we defined it to be something. However, the limit, let's look at this one. The limit as x approaches 0 of sine of 1 over x does not exist. So the limit as x goes to 0 of sine 1 over x does not exist. This is one of those that oscillates. The limit does not exist, therefore it is not continuous. Now, let's look at this function. H of x is x sine 1 over x when x does not equal 0, and it is equal to 0 when x does equal 0. Now, we've already shown, using the squeeze theorem, that the limit as x goes to 0 of this thing is 0. So the limit as x goes to 0 of negative x is equal to the limit as x goes to 0 positive x, which is 0, and negative 1 is less than or equal to sine of y, which is less than or equal to 1. So negative 1 is less than or equal to sine of 1 over x. All right, and now if I multiply, you know what? Which one do I want? I really want the absolute value of x. So let me put absolute values in here because I want to be able to multiply through by a positive number. So minus the absolute value of x is less than or equal to x sine 1 over x is less than or equal to the absolute value of x. And then I want to take the limit of this. So if I take the limit as x goes to 0 of all of this, I get, I'll write it out for you. I'm running out of room. Ah, crud, I forgot my limit, didn't I? Yeah, don't do that. Let me undo, actually. See, teachers make mistakes all the time. Let me start from here. Does that sound fair? I'll do it in red. So the limit as x goes to 0 of minus the absolute value of x is less than or equal to the limit as x goes to 0 of x sine 1 over x is less than or equal to the limit as x goes to 0 of x. So because those limits are 0, therefore by the squeeze theorem, the limit as h goes to 0 of h of x is 0. And as a matter of fact, the value of h at 0 is also 0 because that's the way we defined it. Therefore, this function is continuous over the entire real line.